in a spring control governor of Hartung type. Okay, now the governor is given as Hartung type. The length of the ball and sleeve arms are 80 millimeter and 120 millimeter respectively. Right? The length of the ball arm is 180 and sleeve arm is 120. The total travel of the sleeve is 25 millimeter. In the mid position, each spring is compressed by 50 millimeter and the radius of rotation of the mass center is 140 millimeter. Each ball has a mass of 4 kilogram and the spring has a stiffness of 10 kilonewton per meter of compression. The equivalent mass of the governor gear at the sleeve is 16 kilogram. Neglecting the moment due to the revolving masses when the arms are inclined, determine the ratio of the range of speed to the mean speed of the governor. Find also the speed in the mid position. So this is a question. Now we are expected to find the moment, including the moment due to revolving masses when the arms are inclined. Determine the ratio of the range of speed. Right. So the range of speed we need to find the maximum speed and the minimum speed to the mean speed of the governor. Find also the speed in mid position. Right? So these are the things we need to find. So let's put these data into format, right? X 80 millimeter. So we know this is ball arm, that is 80 millimeter, and sleeve arm is 120 millimeter. So Y, that is sleeve arm, it is 120 millimeter. H. So the total travel of the sleeve is 25 millimeter, right? So the total travel of the sleeve is 25 millimeter. So H is 25 millimeter, and we know H is H1 plus H2, right? So total travel of the sleeve is 25 millimeter. In the mid position, each spring is compressed by 50 millimeters. So in the mid position, so this is a mid position, the spring is compressed by 50 millimeter. Okay, so initial compression, that is 50 millimeter. And the radius of rotation of the mass center is 140 millimeter. So radius of rotation is 140 millimeter, that is R is equal to 140 millimeter. Mass of the board is 4 kilogram, right? Mass of the board is 4 kilogram. And the stiffness of the spring is 10 kilonewton per meter, right? So stiffness is 10 kilonewton per meter, that is 10 into 10 power 3 newton per meter. All right. And the equivalent mass of the governor gear at the sleeve is 16 kilogram, right? So M, capital M is 16 kilogram. We know that the mass of the sleeve is necessary. So here it's given equivalent mass of the governor gear at the sleeve, right? So whatever the parts which are attached to it, the complete mass of it is 16 kilogram. Okay. So these are the given data. Neglecting the moment due to the revolving masses when the arms are inclined. So it is given, we can neglect the moment due to the revolving mass when they are inclined. So we know when we are taking moment about O, right, in mid position, the mass which would be located here won't affect this. Why? Because the action of force is through O, so which will be 0. But when we consider this position, minimum position, right? So mass would be here, right? The mass would be here, ball mass, which will act this way, right? So mass would be here, so which means the mg would be this way. And this mg has a small distance from O to the line of action, right? So while calculating moment, we need to consider that also. But in this question, it is given, we can neglect that. The neglecting the moment due to the revolving masses, we can calculate. So actually, the mass is going to be somewhere here, right? The mass is going to be somewhere here, like this. So which means give some mg, right? So this mg will act this way. So this is a distance between this mg from O, right? While calculating the moment, right? So if this statement, if it is not given in the question, we have to calculate that also, right? But here in this question, it's given, you can neglect that. So we are not going to consider the mass when it is in the either minimum or maximum position, right? So here's a question and here is our data, right? Now we are going to solve it. Let omega the mean angular speed in radian per second, right? So we are going to put them into usual notation. So omega mean angular speed, capital N is mean speed in RPM. We know that the centrifugal force acting on the ball spring, right? So now we are going to calculate the centrifugal force FC. FC is equal to mr omega square, right? So it is given the ball mass is 4 kilogram. Omega squared is unknown, we have to find, and radius is given 0.14. Right? So when you calculate it, you will get 0.56 omega squared Newton. Right? So centrifugal force is 0.56 omega squared Newton. And the spring forces, right? So spring forces, we know it is stiffness into initial compression when it is in the mean position. Right? So in this mean position, the spring force S is equal to stiffness of the spring into initial compression. So how much is that stiffness? It was given 10 kilonewton per meter, that is 10 to the power 10 into 10 to the power 3 Newton per meter into initial compression that was given 50 millimeters, so that is 0.05 meter, right? So when you multiply that, you will get 500 Newton. So you have this spring force at the mean position, initial position, it is 500 Newton, right? So now we'll find the omega squared. How can we find? We'll take moment about O, right? Now taking moments about point O, right? Point O, neglecting the moment due to the revolving masses we have, right? So it was given in the question, you can neglect the motion or movement due to the revolving mass, right? So this mass we can neglect. So what else we have? We have a force Fc, that is centrifugal force. We have an S, that is spring force, and we also have mg at the sleeve. So there are three forces, right? Fc, centrifugal force, S, force by spring, and mg, weight of the mass, weight of the sleeve, right? So we'll put in the equation. Okay, so we'll take moment about point O. So if you consider it clockwise, you have Fc acting anti-clockwise, S acting clockwise, and mg by 2 acting clockwise. So mg by 2 clockwise, S clockwise, and Fc, it is anti-clockwise, right? So Fc into x. So we know Fc is centrifugal force, and distance for it is x. Right? So this is the distance of Fc. So Fc into x is equal to S, which is in the clockwise direction. So equal to S into same distance, that is also x. Right? So S into x plus mg by 2 is acting here, and the distance for that is y. Right? So action here mg by 2 into y. Right? So mg by 2 into y. If you solve it, Fc we have already found it is 0.56 omega squared. Right? So Fc is equal to 0.56 omega squared into x. Distance x was given in the question 0.08. Right? Ball arm is 80 millimeter. 0.08 equal to S. S is spring force, which we have already found as 500 Newton. Right? So 500 Newton into same x, that is 0.08 plus mg by 2. M was given the equivalent mass of the at the sleeve is 16 kilogram. So 16 into gravity 9.81 by 2 into y. So y distance was given, the sleeve arm is 0.12 meter, right? 0.12. All right. Why there's a 2? Because we are solving only the half of this governor, right? Because the full governor would be there's another arm this way, right? There's another ball this way. So we have to solve like this, right? So which we are not going to do. So we will take only half of this one, and that's why there is a 2, right? So when you solve it, you will have 0.56 omega squared into 0.08 equal to 500 into 0.08 plus 16 into 9.81 by 2 into 0.12, which will be equal to 49.42. Okay. So omega squared is equal to 49.42 upon 0.56 into 0.08. Okay. So which will give you 1103. So omega squared is equal to 1103. So omega is equal to 33.2 radian per second. Okay. If omega is 33.2 radian per second, we know to find n RPM, we need to multiply it by 60 and divide it by 2 pi, right? So which will give you 317 RPM, right? So we now found that the mean position, the omega is 33.2 and n at RPM is 317. Okay, so this is the angular velocity at mean position. The question asked is to find the ratio of the range of speed, right? So if we have to find the ratio of the range of speed, we have to find the maximum as well as the minimum speed, right? So we need to find the omega or maximum, that is omega 2, and omega for minimum, omega 1, we need to find them also. Right? So let us assume omega 1 is the minimum angular speed in radian per second at minimum radius of rotation r1, and omega 2 is maximum angular speed at radian per second at maximum radius of rotation r2. So these are usual notations we take, right? At minimum position, the angular velocity is omega 1, radius is r1. Similarly, at maximum position, the angular velocity is omega 2, and the radius is r2. And n1 and n2 are corresponding minimum and maximum radiuses in speeds in rpm, right? So these are our usual notations. Okay. So now we will calculate it in the similar way. Okay. The minimum and maximum positions shown in this figure respectively. First of all, let us find the minimum speed. So we need to find first the minimum, and then need to find the maximum, and then we need to find the range. Right? So minimum speed will translate in 1. So here is a diagram for that. Okay, so we know at minimum speed the balls would be tilted inside, and the sleeve would be somewhere here. Right? Based on the geometry, we can see that a1, right, this one, and a1 upon x is sine theta, right, sine theta 1. So if you consider sine theta 1 opposite a1 upon hypotenuse x. Similarly, here also it's theta, right? So here theta 1 is equal to opposite h1 upon hypotenuse y, right? So since both are theta 1, we can say a1 upon x is equal to h1 upon y, right? So in that case, a1 can be replaced by r minus r1, right? R minus r1. So r is the radius at mean position, and r1 is the radius at minimum position, right? So r minus r1 is equal to a1. So we can put r minus r1 upon h1, right? Upon h1 is equal to x, right? Hypotenuse x upon hypotenuse y, right? So x upon y. Based on this, we can find r1. So r1 is equal to r, right? R1 is equal to r minus h1 into x plus x upon y, right? R minus h1 into x upon y. So when you substitute with the given data, we know r is equal to 0.14. The radius at mean position, it was given as 14 millimeter, that is 0.14 minus h. So h is the total sleeve movement. So that was given as 25 millimeter, that is 0.025. But here it is only the half of the movement, right? Total h is 0.025, but here only h1 we are calculating. So another h2 is also there, right? The other part, right? So we are calculating it 0.025 by 2 into x upon y. So x, the length of ball arm, that is 0.08, and y, that is 0.12, right? 0.12. When you solve it, you will have 0.132 meter. So r1, right? R1, that is radius while rotating at minimum speed, is 0.132 meter. Okay. We know that the centrifugal force at the minimum position. So now we are going to apply the force formula, centrifugal force. So Fc1 is equal to m omega 1 squared r1, right? So since at minimum position, it is C1, that is centrifugal force 1, omega 1 squared and r1, right? So we will replace it with the known values. M, that is 4, it was given in the question. Omega 1, we don't know, we have to find, right? And r1, it was given, not given, it was found to be 0.132 meter, right? 0.132. So when you solve it, you will have Fc1 is equal to 0.528 omega 1 square. Okay. So this is one equation. Now we have to find the spring force. So that then we will move to the moment equation, right? So for that, we need to find the spring force. The spring force at the minimum position, right? So spring force is S1 at the minimum position. So to find spring force, we should know the stiffness of the spring as well as the distance, right? Distance, it is compressed or expanded. Right? So stiffness was given 10 kilometers, that is 10 to the power 3. That's okay. And now the length or compression or expansion, we need to find that. So here the ball is inside the mean radius, right? So here the compression was it was given in the question that 0.05, right? At mean position or at the initial position, the compression was 0.05. So we need to deduct this length from this initial length, right? So that is 0.05 minus, okay, minus, we need to find, we need to deduct this length, that is A1. So A1 we know R minus R1, right? So R was given 0.14, right, in the question. R1 we have found that 0.132, right? So R minus R1 is equal to 0.14 minus 0.132, right? So to find the spring force, we need to multiply the stiffness with the expansion of compression. So now we have found the expansion of compression to be 0.05, that is initial compression, minus this length, that is A1. So A1 is equal to R minus R1, that is 0.14 minus 0.132, right? R is given 0.14, 14 millimeter, and R1 we have already found 0.132 into stiffness. It was given in the question 10 into 10 to the power 3 Newton meter, right? Newton per meter. So when you solve it, S1 is equal to 420 Newton, right? So this much meter into 10 into 10 to the power 3 Newton per meter will give you 420 Newton. So now we have found the spring force. How much is the spring force? 420 Newtons minimum. So now we can apply the moment equation, right? Now taking moments about the fulcrum O, right? Fulcrum O, neglecting the obliquity of arms, right? So obliquity of arms means taking x1 as x and y1 as y. So we know if this is x1, right, with the tilt of this arm, there could be small change on this length, right? Similar way, if this is y, there could be small change with the tilt of theta1, right? So what we'll do, we will usually neglect them if it is not provided, right? If it is exactly provided, you have to consider, then we have to consider. Since it's not provided, we can usually neglect them. So we'll neglect them, right? Neglect this obliquity effect. So we'll consider this y1 as y and x1 as x, right? So now we'll put it in the formula FC1, right? So now we have three forces on this ball, that is FC1, which is the centrifugal force due to the motion, right? And we have S, that is spring force, and mg due to the weight of the sleeve, right? So if you take moments about O, right, FC1 is in anti-clockwise direction, that is centrifugal force in anti-clockwise direction. S1, spring force is in clockwise direction, and mass or weight of the sleeve also in clockwise direction, right? So I'll put it in the formula FC1 into x, right? So FC1 into this length x, it's actually x1, but we are considering x as x1, right? Will be equal to S1, right? S1, that is spring force, into that length x, that's also same, right? Y, they are acting on same height. Will be this one plus mg by 2, right? So the weight of the sleeve, that is mg by 2 into the distance y. Y is 0.08, no, 0.12, right? So we'll apply these terms in numerical values. So FC1 we have already found that 0.528 omega 1 squared, right? 0.528 omega 1 squared into x. So this x distance is given as 0.08 will be equal to S1. S1 now we have found that it's 420 Newton, right? So 420 into length x, that is again 0.08 plus mg by 2, m16 sleeve, equivalent mass of sleeve is 16 kilogram into g 9.81 by 2. Why? Because we are considering only half of the given system, right? Only half of this given system into this length y, that is 0.12, which was also given in the question. So when you solve it, you will have 43.02. So omega 1 squared is equal to 43.02 divided by 0.528 into 0.08. Okay. So omega 1 squared can be written as 43.02 divided by 0.528 and 0.08. When you solve it, you will have 1019, right? 1019. And from this, you can find omega 1 is equal to 32 radian per second. Okay. So if omega 1, that is at minimum position, the angular velocity is 32 radian per second. From this, you can find the N1 at RPM, that is 32 into 60 by 2 pi, which will give you 305.5 RPM, right? So this is the RPM at minimum position. We are asked to find the range of the governor, right? So we need to find maximum position also. Now we have found the minimum position. So now we have to find the maximum position also, right? So similar way, right? Similar way, we will calculate for maximum position also, right? Let us find the maximum of speed n2. So we have to find the maximum n2. Okay. So as we have seen already, theta 2, right? So this is theta 2, and this is also theta 2, which means this length a2 and this length h2. Similarly, this length x and this length y are comparable, right? So based on that, we'll write. So sine theta 2 is equal to opposite a2 upon adjacent x. Okay. Here sine theta 2 is equal to opposite h2 upon adjacent, not adjacent, hypotenuse y, right? Here a2 upon hypotenuse x, here h2 upon hypotenuse y, right? So we can write it as, write this a2, right? This a2 as r2 minus r, right? So this a2 can be written as r2 minus r. R2 is the radius at maximum position and R is the radius at mean position, right? So this A2 will be written as that. So instead of A2, we can put R2 minus R, right? R2 minus R upon H2, right? H2 will be equal to X upon Y, okay? So this ratio is equal to this ratio. This is simple geometry, right? So from this we can find R2 because R2 is an unknown quantity. So R2 is equal to R plus h2 into x upon y, right? So r plus h2 into x upon y. R was given in the question 0.314, right? 0.14 plus h2. So we know the sleeve movement, total sleeve movement is 25 millimeters. So h2, that is half of that. So we will divide it by 2, 0.025 by 2 into x. X was given in the question 0.08, y which was given in the question 0.12. Okay. So when you solve it, you will get R2 as 0.148 meter. Okay. So R2 is equal to 0.148 meter. So now we'll take the centrifugal force, we'll calculate it, FC2, right? So FC2 is centrifugal force at maximum position. And we know that FC2 is equal to mR2 omega 2 squared, right? mR2 omega 2 squared. So m, which was given in the question, 4 kilogram, omega 2 squared, which we have to find, we don't know. And R2 now we have found as 0.148. So FC2 is equal to 0.592 omega 2 squared. Right? So centrifugal force at maximum position is 0.592 omega 2 squared. Okay. So now we have to go for the moment calculation. For that, we first need the spring forces. Right. So S2, right? Now we have to find the S2. So spring force S2 is equal to stiffness S into the compression or contraction distance, right? So that is initial compression plus, right? So here at mean position, the initial compression was given in the question as 0.05 meter. Now there is an extra expansion, that is A2. So A2 can be written as R2 minus R, right? So R2 we have found 0.148 meter. R, which was given in the question, 0.14. So which will be 0.08. So we'll write it. So initial compression, that is R 0.05 plus A2. So A2 can be written as R2 minus R, that is 0.148, right? R2 minus R, that is given in the question 0.14 into stiffness, which was given in the question 10 kilonewton per meter, that is 10 into 10 to the power 3 Newton per meter. When you solve it, you will have 580 Newton. So S2, which is the centrifugal, spring force at maximum position, is 580 Newton. Okay. So since we know the S2, which is the spring force at maximum, we can go for the moment calculation. Right? So now we'll take moments about this fulcrum. Okay. So similar way, we'll neglect the obliquity effect of arms, right? Why? Because while it is here, it was x, but when it moved here, there's a small change in the length, which is x2, but we will neglect it. right? We'll neglect it. So we can find FC into this length x, okay, will be equal to S2 into this length x plus mg by 2 into this length y, right? By taking moments, because FC is in anti-clockwise direction and S is in clockwise direction, mg is also in clockwise direction, right? So FC into x is equal S2 into x plus mg by 2 into y, right? So mg by 2 into y. When you substitute all these values, FC2, which we have found to be here 0.592 omega squared, right? Omega 2 squared, 0.592 omega 2 squared into x, which was given in the question, 0.08 Bolam, equal to S2. S2 now we have found that 580, right? 580 into x, that is length of Bolam 0.08 plus mg by 2, right? Since we are dealing with only half of the system, that is mg by 2, 16 into 9.81 by 2 into that length y1, y2, that is 0.12, right? So y is equal to y2, that is 0.12. So when you solve it, you will have 55.82. So 0.592 omega squared into 0.08 is equal to 55.82. Okay. So omega 2 squared is equal to 55.82 upon 0.592 into 0.08. Okay. So when we solve it, we will have 1178. Okay. Omega 2 squared is equal to 1178. And therefore omega 2 is equal to 34.32 radian per second. So if the omega is 34.32 radian per second, we can find the N2, that is in RPM, 34.32 into 60 by 2 pi, which is equal to 327.7 RPM. Okay. So this is the N2. And the question asked was to find the range of the speed. Right. So the range of the speed is the range between minimum and maximum positions. At minimum position, we have found that it is 305.5 Newton, 5 RPM. And at maximum position, we have found that it is 327.7 RPM. So the range is maximum minus minimum, which is equal to 22.2 RPM. Right, 22.2 RPM. And now the ratio of range of speed to the mean speed. So it was given. The question was asked, find the ratio of range of speed. Right, so this is the ratio range of speed and the mean speed. So mean speed we have already found that 317, and the ratio is has to be found, right? So this is 22.2 RPM, right? N2 minus N1, that is a range 22.2, and the mean speed we have already found that 317, right? So 22.7 by 317, that is equal to 0.0707%, right? So this is the answer. So the question was to find the ratio. So that's why N2 minus N1, that is range of speed, and the mean speed, N, that is mean speed, and this is the ratio, right? So this ratio is 7%. Okay.